The concept is especially important in Gromov's geometric group theory. Definition: suppose that is a function from one metric space to a second metric space, then is called a quasi-isometry from two if there exist constants, and such that the following two properties both hold. For every 2 points and in, the distance between their images is within a factor of their original distance. More formally, every point of is within the constant distance of an image point. More formally, the two metric spaces are called quasi-isometric if there exists a quasi-isometry from two. Examples: the map between the Euclidean plane and the plane with the Manhattan distance that sends every point to itself is a quasi-isometry. In it, distances are multiplied by a factor of at most. The map that sends every tuple of integers to itself is a quasi-isometry. Distances are preserved exactly, and every real tuple is within distance of an integer tuple. In the other direction, the discontinuous function that rounds every tuple of real numbers to the nearest integer tuple is also a quasi-isometry. Each point is taken by this map to a point within distance of it. So rounding changes the distance between pairs of points by adding or subtracting at most. Every pair of finite or bounded metric spaces is quasi-isometric. In this case, every function from one space to the other is a quasi-isometry. Equivalence relation. If is a quasi-isometry, then there exists a quasi-isometry. Indeed, may be defined by letting be any point in the image of that is within distance of, and letting be any point in. Since the identity map is a quasi-isometry, and the composition of two quasi-isometries is a quasi-isometry, it follows that the relation of being quasi-isometric is an equivalence relation on the class of metric spaces. Use in geometric group theory. Given a finite generating set S of a finitely generated group G, we can form the corresponding Cayley graph of S and G. This graph becomes a metric space if we declare the length of each edge to be 1. Taking a different finite generating set T results in a different graph in a different metric space. However, the two spaces are quasi-isometric. This quasi-isometry class is thus an invariant of the group G. Any property of metric spaces that only depends on a space's quasi-isometry class immediately yields another invariant of groups, opening the field of group theory to geometric methods. Examples of quasi-isometry invariants of groups. The following are some examples of properties of group Cayley graphs that are invariant under quasi-isometry. Hyperbolicity. A group is called hyperbolic if one of its Cayley graphs is a delta hyperbolic space for some delta. When translating between different definitions of hyperbolicity, the particular value of delta may change, but the resulting notions of a hyperbolic group turn out to be equivalent. Hyperbolic groups have a solvable word problem. They are B-automatic and automatic. Indeed, they are strongly geodesically automatic, that is, there is an automatic structure on the group, where the language accepted by the word acceptor is the set of all geodesic words. Growth. The growth rate of a group with respect to a symmetric generating set describes the size of balls in the group. Every element in the group can be written as a product of generators, and the growth rate counts the number of elements that can be written as a product of length n. According to Gromov's theorem, a group of polynomial growth is virtually nilpotent, i.e., it has a nilpotent subgroup of finite index. In particular, the order of polynomial growth has to be a natural number, and in fact, if grows more slowly than any exponential function, g has a sub-exponential growth rate. Any such group is amenable. Ends. The ends of a topological space are, roughly speaking, the connected components of the ideal boundary of the space. That is, each end represents a topologically distinct way to move to infinity within the space. Adding a point at each end yields a compactification of the original space, known as the end compactification. The ends of a finitely generated group are defined to be the ends of the corresponding Cayley graph. This definition is insensitive to the choice of generating set. Every finitely generated infinite group has either one, two, or infinitely many ends. And Stalling's theorem about ends of groups provides a decomposition for groups with more than one end. Amenability: an amenable group is a locally compact topological group G carrying a kind of averaging operation on bounded functions that is invariant under translation by group elements. The original definition, in terms of a finitely additive invariant measure on subsets of G, was introduced by John von Neumann in 1929 under the German name of Messbar, in response to the Banach-Tarski paradox. In 1949 Marlon M. Day introduced the English translation, amenable, apparently as a pun. In discrete group theory, where G has the discrete topology, a simpler definition is used. In this setting, a group is amenable if one can say what proportion of G any given subset takes up. If a group has a Follner sequence, then it is automatically amenable. Asymptotic cone: an ultralimit is a geometric construction that assigns to a sequence of metric spaces Xn a limiting metric space. An important class of ultralimits are the so-called asymptotic cones of metric spaces. Let be a metric space, let omega be a non-principal ultrafilter on unless Pnx be a sequence of base points. Then the omega ultralimit of the sequence is called the asymptotic cone of X with respect to omega, and N is denoted. One often takes the base point sequence to be constant. Pn equals P for some Px. In this case, the asymptotic cone does not depend on the choice of Px and is denoted by or just. The notion of an asymptotic cone plays an important role in geometric group theory since asymptotic cones provide quasi-isometry invariance of metric spaces in general and of finitely generated groups in particular. Asymptotic cones also turn out to be a useful tool in the study of relatively hyperbolic groups and their generalizations.